Sure, we're recording. Thank you all for coming to the Math Mondays bonus session. Tonight, Mike is going to be talking about geometry, and as always, we will be sending out the recording tomorrow, and you can also view it on our YouTube page. So I'm going to throw the link in the chat, and if you all are able to or would like to, you should subscribe to our YouTube channel where we have weekly video updates, and then all of the Math Monday sessions are hosted there as well. So with that, if there's any questions, you can also put them in the chat, but make sure you guys stay on mute and Mike can take it away.
Hey, thanks, Aaron. Thanks, Taylor. Appreciate that. So tonight we're going to talk about geometry and just why it's really important. And I know that in different countries, talking to people from around the world, the way that geometry is treated differently in different areas of the world. Here in the United States, it's often seen as something where it's kind of done in high school or maybe for advanced students, and it's something that generally doesn't get a lot of notice for the younger adolescent, especially. And what's interesting is that if you look at it from a Montessori perspective, though, geometry is being done all the time. Geometry is being done for the very young child, and it should be done all the way through elementary and all the way through adolescence. And so I'm going to talk a little bit about how we can do that, why it's so important, and how we look at geometry for the older child. But to start off, though, I'm going to start with a joke because it's going to be fun, and it's going to be really, really funny. So if you're not sure if it's funny, I'm telling you, you're going to laugh at the end, and then if you don't laugh, then well, it's not because it's not the joke's fault if you don't laugh. Okay, so a mathematician, a physicist, and an engineer were traveling through Scotland when they saw a black sheep through the window of the train. Okay. So there he is right there. And aha, says the engineer, I see that Scottish sheep are black. Says the physicist. You mean that some Scottish sheep are black? No, says the mathematician. All we know is that there is at least one sheep in Scotland, and that at least one side of that one sheep is black. So it's a funny joke because, okay, I'll tell you why this is funny. It's because mathematicians have a tendency to overanalyze, to be over precise with things. And in this case, that's really kind of going to, even though technically the mathematician is correct, I do have to defend the mathematician here, that if you only see one sheep and you only see one side of it, then all you know for sure is that there's one sheep and one side of it's black. However, in practicality, in reality, that's not a very good definition. Now, if you look back at what the engineer says, he says, I see that Scottish sheep are black. Now, there's an overgeneralization right there. I mean, that's dangerous to assume that just because you saw one sample of something, that's going to be true in all cases. And I hate to admit it, being a mathematician, but I think the physicist has it right. That right level of reality versus precision, where he says, you mean that some Scottish sheep are black, whereas like you're acknowledging that there may be others, but we don't know. We're not being that precise. And I think we kind of want to have that middle attitude, I think, a lot of times when we do geometry with our adolescents. It seems that sometimes in mathematics in general, we can get, especially when you have mathematicians, people who are mathematicians teaching children, where they come at it from a very formal place, a place of precision. And oftentimes that really clouds the actual issues and really gets in the way of understanding rather than refining the understanding. It's like when Montessori says, to teach details is to bring confusion. To teach the whole is to bring learning. To teach details is to bring confusion. And sometimes mathematicians have a tendency to get so deep into definitions and precision and the details of it that we kind of lose what the big picture is. So I just wanted to mention that as we're starting off here. So what we're really talking about, and geometry is a great way to do this with the students, is we want to help them form their mathematical minds. And so when we talk about the mathematical minds, we can mean a lot of different things. But one thing we think about with the mathematical mind, pardon me, is to be precise. We do want to be accurate with what we're saying. Um, Precision can, though, as I said in the previous joke, can sometimes get in the way of understanding. And so I like to think about it as being as precise as necessary for the age of the student, and then refining that through student experiences and through and then through the mathematical maturity of the student, we can get more precise as we go along. So oftentimes, if we have a definition that seems to suffice, the students understand it and it works, then we'll go with that definition. But if the definition isn't precise enough, then suddenly, there'll be exceptions or things that don't seem to make sense. Then we need to go back and revisit that definition and refine it and give that level of precision when it's necessary to do so. But we don't want to do that precision when it's not necessary, or it won't be helpful for our students. The mathematical mind also deals with things like exactness and order and the imagination, where we're able to, by the imagination, it's not this wild imagination, but it's being able to make an image of something, to hold ideas and concepts that exist, and then to create images of those, to be able to manipulate ideas mentally, but the ideas are always rooted in reality at some level. And the other thing that we want to keep in mind is that while mathematics is an expression of the mathematical mind, not everyone expresses their mathematical mind through mathematics. And so to me, focusing in on the mathematical mind through mathematics, through geometry especially, mathematics is not always the end game. So for example, we want all of our students to be able to have exactness, to be precise, to have an ordered mind. Like that's something that you need just in life to function well in society. Some people do it through mathematics as well, but not necessarily. And so to me, why I think teaching mathematics is really important is partially because of how it helps the student's development, how it helps that aspect of their personality to grow. And we need to continue to keep that in mind from front and center whenever we're doing work with a subject area, is how does this help develop the development of the person right in front of me. So one thing that we want to do is we want to see geometry as a psychodiscipline. And this is Montessori's term for how she approaches the disciplines. The disciplines are things like the subject matter and the methods we use to engage it. But the psycho part in the front is really about the psychology of the child in front of us. And so we present different aspects of the subject matter of the discipline. We present it in different ways and have different expectations for what the students will do with that, depending on their age groups. And so I put together a really simplistic chart here. The spiral on the right is there to indicate the fact that we keep revisiting topics over and over again, but we do it in new ways. And if I just take an example in geometry, something like shapes. Okay, when we study shapes, let's say the triangle, for example, that's geometry is there for the 3 to 6 year old. But what is it that the young child is really getting with their shapes, with triangles? They're learning the names of those words. It's very natural for them, and they do it in a very specific way. They'll take the metal insets. There'll be very little speaking during the lesson, but it's more by showing. Taking their fingers and rubbing it along the outline of the shapes and doing tracing. And they're associating the word with how it feels. And what's interesting about that is, if you think of a word like rhombus, that's a word that a lot of adults say, oh gosh, that's a really complicated word. I can't believe kids learn rhombus at such a young age. But when you think about it, the word rectangle has like 3 syllables. Like that's a more complicated word than rhombus, but yet rectangle seems very natural to us. It's like, oh, it's just a rectangle. And so just for us as adults, why does rectangle, I'm speaking very generally, of course, why does rectangle seem like a word that's very natural and rhombus seem like a very unnatural word? And I think it's because of when we probably learned those words. I didn't go to a Montessori school, and I didn't learn the word rhombus until much later. So in a way, it's not as ingrained in my being as the word rectangle, which is something I learned when I was a kid. Um, and so there's nothing inherently difficult about these. It's just that are we presenting that vocabulary at the right time? And if you do that, it has a stronger hold. It affects the child in a different way. And there's other things that happen in age 3 to 6, but one strong thing when they do geometry is they're really learning the vocabulary. They're learning to identify what shapes are. They're learning to identify, um, and basically just name things around them. But then when they get a little bit older, they start to examine a little bit more. And this goes to something that's naturally happening with elementary students, where they're able to use their imaginations, and they start to do things like look at the properties of things. So what makes this a triangle? Before, they just saw a triangle and they knew it was a triangle. But now it's like it has three corners, and it has three angles, and it has three sides and three vertices, and there's all this vocabulary that we're still learning then as well. Although we'll learn the vocabulary in a new way, a way that's more appropriate for the elementary child, and we're learning that vocabulary through studying the properties. And so we'll do things like sorting and classifying, like, hey, these triangles all have a really big angle. That's an obtuse angle. Let's sort all the obtuse triangles and all the acute triangles and all the right triangles and the smalls and the larges. And we do all these activities to really bring out those properties. So they're using shapes. They're studying shapes, but they're studying it in a new way. And then when this child gets a little bit older, they start to experiment more and come up with theories and test those theories and really act like a scientist would. And so they might do an activity with the triangle where they have paper triangles, and they tear all the corners off the triangles. And if you actually line those up, put them, connect all the vertices together, they'll actually make a straight line. And then they do it with another triangle and another triangle, and they experiment, and they're like, wow, that actually works. And they can discover through experimentation these rules and these laws about geometry, such as the sum of every interior angle of a triangle adds up to 180 degrees. That's something, though, that they discover through experimentation. And that's really appropriate for them to do at that age. And so often we see in mathematics at the elementary level in Montessori, we see that rules are the point of arrival. That's where students get to. They manipulate materials, they do experiments, they observe, they do writing, they do talking about it. And then when they're done, they say, oh my gosh, I've discovered something that is always true. And they can explain why the formula happens. We see this all the time with area formulas. They do it practically at first, and then they discover the formula, which is basically just a shortcut way of them saying their thought process. So now we come to the 12-year-old or the younger adolescent. And this human being is very different than the previous human being that we see in front of us, even though they might, they're the same actual people, but they've grown up and they have different needs. They have different interests, which is totally appropriate, and that's really, really good. But the question that the 12 to 15-year-old often asks is, what's in this for me? How does this apply to my life? And that's a totally appropriate question for this child to ask, because they're starting to see themselves, no longer as a child, but they're in this bridge to adulthood, and they want to know where their place is in the world. How do I fit in my society? How do I fit in my community? And if I want to participate in that, I need things for me. And now they can say, hey, how does this fit in for me? So now all of a sudden, if you try to do things with triangles, they want to know, well, what good is a triangle? What has a triangle ever done for me? So the most appropriate thing we can do for geometry at this age is have them apply things, have them use geometry to do work. So they can do all the things they've done before. They know the vocabulary, they understand the properties, they understand through induction, they understand certain rules that they've done. Now it's time to put that into action. And they can do this in all kinds of ways. So students applying geometry in things like design. where they have a small business and they're doing logos, and they're on the computer, or they're doing it by hand, and they're doing different design elements to put that together. We see that in art, where students have this great sensitivity towards art, but we can now analyze the art rather than just analyze the art from a geometric perspective, so they can understand geometry through, because there's a need for it, right? If they're not just studying, let's just study perspective drawing to study it, but let's study it in the way that other people have done perspective drawing, so that you can become a better artist. This way you can express yourself in different ways. Whenever students are building things, they're using geometry, they're dealing with shape, they're dealing with size, they're dealing with volume. They're actually taking what they've learned about it and applying it. And then through their questions that come out in their applications, that's where they're going to get their learning. So it's like, hey, I'm trying to solve this problem. I'm trying to figure this out. Can you help me? Can you explain to me what it is that's happening here? And now we come in with the lessons, because it's directly applicable to what they've done. And then later, as this child moves through adolescence towards the fourth plane of maturity, or more that adulthood, then that's where deductive reasoning starts to come in. They have more of an interest in the philosophy of why things are true, and if things are really true, and how do I really know that things are true. And oftentimes, that's what we think about as geometry, because that's what we did when we were in school. For me, geometry was all about doing 2-column proofs, and it was all done logically, and that's all it was. And it was basically just a bunch of checking and guessing for me, or just not even checking, just guessing. I had to say things like theorem 3.14 and like write that down for my reason. And I didn't know why I was doing it, but that's kind of what the teacher did. And if I kind of memorized what would happen, then I could do that. And somehow that's geometry. And that's really, really hard to do things that way. And that's why I think a lot of people say, well, geometry should really be for the older student, because in some way they're only thinking of deductive geometry, geometry that's done, by only doing proofs. And really, that's a small part of what geometry is. And it's really not until students are older that they have a sensitivity towards that. So now all of a sudden, when you say, the sum of a triangle equals 180 degrees, kids knew that in the induction phase. They learned that in elementary. But then if you take the younger adolescent and you try to prove it to them, and I'll show that in a little bit, they're going to say, why are you showing this to me? You're making it so much more complicated. I already know it's 180 degrees. Why are you wasting my time? Like, I already know this. But that's not what it's about. It's really about, how do you know that? Is it something you just feel is true? There's a certain philosophy behind knowing absolute truth. And so we'll talk about the Greek philosophers and the history of geometry, and do some really cool puzzles and logic, and kind of put this together where the students are really asking the question, how do I know that's true? And now they have more of an interest in the deductive reasoning because they see a purpose for it. It's a different purpose than there was 3 years ago when they were 13 years old. Now it's a purpose of understanding truths and this kind of internal, this kind of metacognition that older adolescents really have a passion for. And so, unfortunately, what happens often is geometry is done for the very young child. They do the vocabulary, they learn their words. And then because of the Montessori materials, geometry is so beautiful and so easy for the children, because it's naturally, it just, when you do algebra or even arithmetic, you have to materialize that abstraction. Like the number 3, like that's an abstract idea, right? So to have 3 things, you're trying to pull the idea 3 out of there. It's like there's like another level of abstraction. But with geometry, a circle is a circle. A rectangle is a rectangle. Like, you are working much more directly with those things. So materials definitely directly reflect the concepts that students are working on. And often what I've seen in the elementary is that because the geometry goes so beautifully and so easily that teachers teach it, the kids love geometry, and they, quote, finish geometry like by the time they're like 7 or 8 years old. And then the teacher says, well, they've had that lesson, no more geometry, because they've done everything. Or arithmetic becomes more important to the kids, and so they don't revisit that geometry, and they miss out on continuing to practice and seeing things in new ways. And so sometimes when I get students who are 15, 16 years old, they haven't had geometry since they were like 7 or 8. And it was only at a very basic level. And so Maybe some of us can do more work with the elementary to help them to continue to, because I know there's kids who, they'll come to me in adolescence and say, I don't know what a rhombus is, but I know they've had that vocabulary because they've had Montessori. But the problem is they haven't used it for 5 years in Montessori elementary. They learned it in primary, and then maybe they did a little bit of work with it in early elementary. But then if you don't keep bringing that up, you're going to lose some of that if you don't keep revisiting it in new and exciting ways. And so my plea here today really is for, why do we do geometry? How can we do it? And just the fact that we're conscious of the fact that we don't lose that. Oftentimes, algebra takes a lot of precedence for the younger adolescent, where they kind of do algebra exclusively. And the reality of it is, so here's a map that I made, just kind of, to help teachers with algebra, because oftentimes I'll teach algebra for 7th and 8th grade. And at the bottom, you see functions, expressions, equations, and this is kind of the algebra thrust of things. But if we look at the top, though, I have things like problem solving, fractions, decimals, percents, estimation, order of operations, probability, statistics, and geometry. These are all things that we should be constantly doing. Maybe you don't have a separate standalone geometry course, you just have a math course, or maybe you have more of an algebra course, but geometry should be happening within whatever you're teaching. The same thing with probability, the same thing with statistics. The same thing with fractions, decimals, and percents. Like there's not an adolescent lesson for decimals. Like when do we teach decimals? The answer is always, or whenever needed. We're always working on those things. And so we should be doing geometry in service to algebra and algebra in service to geometry. Those things really need to go hand in hand. And what's so great is, teachers will often say, well, when would we use something like solving two-step equations? Like, what's a practical example of that? And just the other night, I was teaching a workshop on trigonometry, and we were talking about similar triangles and similarity and doing ratio and proportion. And through trying to solve those, we ended up with solving equations, solving one-step equations for x, solving two-step equations for x, having equations with fractions in them, and having equations with x's on both sides from a very simple, just here's a triangle, find the proportion. Things come up naturally when you start looking at practical problems, and doing that through the geometry is a great way to do that. And so I don't think you necessarily have to have a separate geometry class. In fact, I would say that all these things should be integrated together as much as possible in a natural way. Okay, so I'm going to share with you an example of, I know I mentioned before here, induction is something that's really strong for the 9 to 12-year-old. But that doesn't mean it only stays there. Induction, the idea of experimenting and coming up with formulas, coming up with discovering patterns and doing that work, that's something that actually mathematicians do all the time. That's when I was in graduate school, that's basically what it is too. It's like, hey, here's a situation, go and explore, discover things, and then come up with reasons why. And so that's really the beginning step to any math work that's done is you start experimenting, you look for patterns, and you wonder why these things are happening. And that's where deductive reasoning comes in, which makes us different than science. See, if you're a scientist and you want to ask a question about what's happening to the honeybee population, you see something, you ask the question, you notice that year after year after year the honeybees aren't coming around. So now you're making your observations, and then maybe you set up an experiment. Maybe you put in certain kinds of flowers out, or you keep track of the temperature year by year, and then you discover the migrating patterns of the honeybees and all that kind of stuff. But at some point, though, if you say what's actually happening, what's the real reason behind it, it's hard to get to that deduction to say for sure 100% why something is happening. It's why things are called theories. We can have our best guesses. It's like gravity, right? It's called the theory of gravity. I know that if I drop this pen, it's going to hit the table. There we go. I was right again. It worked yesterday. It's going to happen tomorrow again. But we don't know like we can't give a logical reason why it happens. The reason why it's going to happen is because it always happened in the past. And the more and more it happens, the more likely, the more we believe it. With mathematics, though, we can say, here is the logical reason why it happens. We can take it one step further. But all the work in mathematics and in science always starts with induction. And this is a great way to kind of bridge that gap for our younger adolescents to help them from induction, to get from induction to deduction. Because even though they might not be interested in it, for its own sake, we want to definitely set the foundations of that work through applications, through thinking, through work, and set the foundation so when students are ready for deductive reasoning, they have those techniques and those skills ready to go. So I'm going to do a puzzle with you. I like doing this with, I have a Rubik's Cube, and interesting note about the Rubik's Cube, if you leave it on the windowsill, it will, eventually all the stickers will fall off because it gets hot and then the glue dries up and then they all fall off. So I had this Rubik's Cube. It's, the 3x3x3 cube. That should say 3x3x3 cube. Sorry about that. And so we just start with this question. How many little cubes is this made out of? And we say it's made of 27 little cubes, inside there. And then we say, okay, imagine you take that whole cube and you dip it in paint and you take it and it dries and then you disassemble it. And then we ask the students to use their imaginations and say, how many little cubes will have no sides with paint on it? And the answer for that's just going to be one. Just the one cube in the center that we can't see will have no sides with paint on it. How many little cubes will have paint with one side or with two sides or with three sides? Sometimes I'll even say, is it possible for a cube to have paint on four sides of it? And then, we'll do that work and we'll see how that is. So I'll give the students a chart like this, and then we'll say, go ahead now that you've done it with 3x3. What about 4x4x4, 5x5x5? What happens as you keep building the cube larger and larger? So this is what it'll look like for a 3x3. You'll have that one cube in the middle with no sides that won't be painted at all. You'll have 6 cubes that have one side painted, 12 cubes that have 2 sides painted, and 8 cubes that have 3 sides painted. And just kind of a check, if we add all those together, we do get 27. And I think it's really good that whenever we do work with students, that we have some way for them to verify that they're correct. Now, they might have made a mistake here, and it happens to add up to 27, but it's pretty likely that you've gotten everything if it adds up to 27. Because that's how many little cubes there are. And at this point, I get the students started with this, and then I let them experiment. And I will provide for them little cubes that they can assemble and put together if they want to do it hands-on. Other students just want to use their imaginations. It's really up to them. But especially for our younger students, having that physical model to see what's actually happening is really, really powerful. And so we just want them to experiment and catalog and see what's happening. So as they go through, this is what they'll end up with. And at some point, we say, okay, what's happening here? What's the pattern? What if I gave you a cube that was 37 by 37 by 37? Can you figure out, without making the chart, like what's actually happening? And then the question is why? What's happening and why? And so at this point, students start to look for patterns. And there's a really easy pattern to see for 3 sides. It seems like every cube will have 8 little cubes with 3 sides painted. And if we look for other patterns, if we look at 2 sides, it's going up by 12 every time. Now, it seems to be going up by 12 every time, but do we know that the next one's going to be 12 more? I mean, it seems reasonable because that's what's happening, but how do we know for sure? That's a question that we'll try to answer. If I look at one side with paint on it, that pattern's not so easy to see. I see it's definitely going up, but it doesn't seem like it's a very regular pattern. And so that's when the students really struggle with, which is why I like doing this activity with my students of really any age, because there's some things where they can notice right away and other things where they have to go a little bit deeper. It forces them to think of things inductively. And then for 0 sides, it's interesting to see which kids notice the pattern here. Here we end up with the cube numbers. So we have 1, which is 1 cubed, 8, which is 2 cubed, 27, which is 3 cubed, and 64, which is 4 cubed. So it seems like that if you kept going up, you're going to get the cube numbers there. Okay. So this is something the students will create. They usually work in groups. And right now they're just experimenting and playing, but we want them to be observant as they do this. And here's the thing is we really want to encourage students to not just do things to collect data, but to be thinking as they're doing. That's something we do throughout all of Montessori. When students are working with things like the checkerboard, they don't just use it as a fancy adding machine. They should be thinking about place value and about why the colors are the way they were and how we do the exchanging and all that work. They need to be verbalizing and thinking about those types of things. So I took this picture. These were some cubes that we had. These are Unifix cubes. I gave them to my students to work with. And what I found really interesting is most kids just all used one color or just did it randomly. But one group chose the colors based on how many sides would have paint on them. And so this was the 6 by 6 by 6 cube. And here was their chart. And so now we start to ask them, okay, you said you think or you believe that for every large cube that we make, 3 of the smaller cubes are going to have, sorry, say that again. A lot of numbers here. For every large cube that you make, you think that there's going to be 8 little cubes with paint on 3 sides. And we saw that in the previous thing here, right? 8, 8, 8, 8. The question is, why? Okay, let's say it's going to be 8. Why do you think it's going to be 8? Why do you actually believe that to be true? And from from the work they've done, the modeling, they're going to say, well, the only way that you can have a cube with 3 sides of paint on it is if they're in the corner. And every cube has 8 corners, therefore, there's going to be always 8 cubes with 3 sides painted. And what I just said there, which kids can at a very young age can articulate, that actually is a proof. You gave a proof, a reason why that actually happened. And students can write that out in paragraph form to explain their reasoning. And we're trying to make this jump now from experimentation, right, to the idea of having reasons why and being able to explain those reasons. Okay, so now what do we want to look at next? How about, well, we did 3 sides. Let's look at 2 sides. That seemed to be going up by 12 every time. But what's actually happening here? So we say, well, where are the little cubes that have paint on 2 sides of them? And those are all the white cubes that you see in the picture there. And so I said, well, where are the cubes that are white? Well, they're on the edges. And if this is a 6 by 6 by 6 cube, is the full edge white? Well, no. It's all white except for the 2 corner ones because those are going to actually have 3 on them. So for the 6 by 6 by 6 cube, we have 4 whites on each edge, and we have 12 edges because every cube has 12 edges. Okay, great. So what would happen if I had a cube that was 100 by 100 by 100? What would it look like? Use your imagination. Well, you'd still, for every edge, all those white cubes would be on the edge, except you have 2 end pieces that were red. So you would have 98 on each edge. You have 12 edges. So altogether you'd have 98 times 12. And that's why we see this going up by 12 every time. In fact, for the 6 by 6 by 6 that you see there, notice that the 48 is 4 times 12. It's 4 times 12 because each side had 6. There were 2 that were already red. So you have 4 on each side, and there's 12 edges to the cube. So now, not only can students say, well, there's one thing to find the number, but now they know why the number is what it is. And now let's look at that one side. Remember before that this pattern here was really hard to see what the heck was happening. It's not very obvious, to come up with the next number in this list, yet alone a number way down the list. So where are all the cubes that have just one face painted? Well, those are going to be the orange ones. And where are the orange ones? Well, those are on the faces. But is it the whole face? No, it's not the whole face. It's going to be a square, but you have to take away all the squares on the edges. So here where you have a face that's 6 by 6, since each edge takes up 1 square on the top and the bottom, you're going to have a square that's 4 by 4 on each side. And since there's 6 faces to the cube, you're going to have 4 by 4, which is 16, and you're going to have 16 times 16 times 6, which gives us 96. So imagine, what if you had a cube that was 52 by 52 by 52? What would it look like? Where would the cubes with one side of paint be? You're going to have a square on each face, and each face is 52 by 52, except you're going to have, the square is going to be two smaller than that. You're going to have squares of 50 on each side because the edges, you have two edges on each side of your square. So it's going to be 50 by 50 by 50, 50 squared times 6, whatever that is, 1,500, and they can just do it right there. And I think that's a really important step to do with the students, is to have them use to say, what if? In other words, yes, you see it. Can you describe not what the answer is, but why it's happening? What are you doing all the time? That's really the key. And lastly, zero sides. Well, where are those zero sides? Well, they're inside the cube. We can't really see them. But can you imagine that what would happen if you took away all the cubes that are colored on them? What would you have left? You'd have a little cube in the middle. And what would the edge and the faces of that cube in the middle would match up perfectly with the orange cubes you have right there. In other words, you take off all those layers, you'd have a little 4 by 4 by 4 cube right in the middle. And that's why that's 64. This is something students can come up with. They can definitely extend the chart as much as they want to, but at some point though, the question is why? And then with students, we come up with the formulas for these. Now, the formula is not something that I give the student, nor is it something that that really has any meaning unless the students can explain why. So let's go ahead and do it the same way we just did it. 3 sides. It's 8. Why? Because there's always 8. No problem there. Now, when we see 2 sides and we try to express what's happening with all the ones that have 2 sides, what's happening? Well, if it's 37 by 37 by 37, you're going to have 35 times 12. And why 35? Because it's 37 minus 2. So what's happening here? Whatever size your cube is, you're always taking away 2 to figure out how many fit on an edge. And then you multiply it by 12 because you have 12 edges. That's what that 12 times n minus 2 means. When a student looks at that, they might be able to say this in words. And for younger students, then we can help them with the symbolization. But I would never just give them 12 times n minus 2 and say, that's how you figure it out. It should come from the meaning of the physical work, of the geometric work that the students have already done. For the one side, can you see what that formula actually means now? N minus 2, why? Because you have those edges are a different color. So your square is always going to be 2 smaller than whatever your size is. You square it because that makes your square on one side. And then you multiply by 6 because you have 6 squares. So that's what we're seeing right here. This is 4 by 4. And I don't care that it's 4 by 4. It's 6 minus 2. If it was 37, it would be 37 minus 2. If it was 1,035, it would be 1,035 minus 2. So it's going to be whatever number minus 2, squaring it, multiplied by 6. We have to help students to take their observations that they're making in a natural way and be able to express that first orally, then in writing, and then mathematically. There's a progression that we take students to. And all students might not be ready for all of those levels at the same time. They might only be able to express things orally at first. That's a great start. Let's move on to something else. Other students might be ready to put that down in writing. And then later, other students might be able to put that into the mathematical symbolism. But we want to help them make those connections. But we don't start with the symbolism because that's the pinnacle. That's like the top of the tower. And if they don't have the basis for understanding what it actually means, then giving them that formula is like when I was in geometry class and something said theorem 3.14. Like, I don't know what that means, but it sounded good. The teacher wanted me to say it. We want them to have complete meaning and understanding here. And lastly, the zero sides. Well, again, you're going to have 2 less than whatever side, and you're going to have a cube in the middle. And that's what that means. So they don't just see that as an exponent of 3, but they're literally seeing a cube. You should be able to see all those little formulas at the end there and understand what they mean, where they come from, explain it in words, and visualize what's actually happening. And so there's a lot of things. Geometry really lends itself to this type of activity because there is so much, because the level of abstraction, there's one less level of abstraction because you're already working with geometric concepts physically. Whereas if you're doing algebra, algebra is already you have to materialize that, and then you have to go and express it. But here, though, that cube is literally cubes. The square you see there is literally a square. It's the 12. You can actually count the 12 things in the cube. Like, it's very natural then for students to take things that are happening geometrically and be able to express them because they're already a physical object, which is great. So when we want to use this approach with students in geometry and really in any subject, but when we want to get them to get to this place, we first start with the concrete. Here's some examples. Work with the material. See what's actually happening so you have that experience. Then the next thing we do is we say, okay, now what if? And that's why I love doing that. When the kids do the experiments with like 2, 3, 4, 5, 6 six-sided cubes, or cubes with 6 on each side. What if it was 37? This forces them to understand what's happening in a different way. It's like, okay, they have to use their imagination. And then we say, what's happening? So once they use their imagination, now we get to that abstraction where now we're saying to them, I don't care if the number's 35. Why is it 35? What's actually happening? Oh, we're always taking the edge and we're always taking 2 away. So they're pulling out the essence of what's actually happening from the materials, and now they're able to explain that. So what if is saying, what would happen? What would the numbers be? And then what are you doing? And I love asking that question. That really helps the students transfer to that abstraction. And then finally, present the argument. Explain back what's happening. And that gets to that idea of exactness, where we want that precision. And that's really what the mathematical mind's about. It's not just saying, well, I think this is kind of what's happening. No, like, explain what's going on here. And so we see these different levels of work, and we want to guide students through these and give them and really help them with this approach, because once they get to that exactness, that's the deductive reasoning. Okay. But the truth is, students can do deductive reasoning very early on if it's not presented, if it's not done so abstractly. If it's done more concretely, where they can explain what they're seeing in front of them, they're more likely to be able to explain things and to kind of write a quote proof, but really it's just an argument or a justification for their work. And then later, when they have the mathematical maturity, they can apply it to more abstract ideas rather than necessarily coming from something that's so concrete. And then what I like to ask students is to verify, right? This is what you do when you're a scientist. Okay, you have a formula now for 6 by 6 by 6. Does it hold for 7 by 7 by 7? And test it. So instead of making the cube, plug the numbers into the formula, see what numbers you get, and then build it and see if you're right. And then what happens if you have a 2 by 2 by 2 cube or a 1 by 1 by 1? And here the formula actually breaks down. It doesn't work, but they can explain why. So now they can refine things. So they can say, instead of just having that formula like we had, they would say, this is a formula for finding the number of sides of a cube that would be painted for a cube that's 3 by 3 by 3 or larger. See, that's a level of precision that we didn't have before, because it won't work for 2 by 2 by 2 or 1 by 1 by 1. But if we throw all those details in right away, that's too much. So what we do is we do the work, we then give our arguments, and then we refine. Okay, so now it's only going to work for cubes that are 3 by 3 by 3, but do you know it's always going to work for something larger? Yes, and here's my reasons why. So as I mentioned before, some of the interior angles, this is the activity that students will do. They'll cut those corners off, they'll line them all up, 180 degrees. And honestly, this is so good. Like, if a student doesn't know it's 180 degrees, I don't care what age they are, this activity is going to help you remember that. Because once you do that, I remember the first time I saw it. No, I don't remember the first time I saw it, but I know I was at least in college, if not graduate school, when I saw this for the first time. And I was just like, oh my gosh, it is so cool. Like, how is it? Like, even though I knew it was 180, the fact that you actually tear those off and rearrange them and to make that into a straight line, Like that visual will always stay with me. So if my goal is to remember that the sum of a triangle equals 180 degrees, this experiment is plenty good. And the kids do this in elementary, and I do this again with my kids in adolescence. Here's the formal proof for the sum of the interior angles. Now, this is absolutely beautiful and wonderful in its own way. However, if I'm trying to remember what the sum of the interior angles of a triangle are, and I want to remember that it's 180, this picture is going to be much more useful than remembering this proof. I mean, honestly, I can just see it. Here, there's reasoning, but this is really the reason why. If you just said, do you know for sure, how do you know you're not going to come across some triangle someday that doesn't work for? You don't know that. But here we can give a logical reason of why it must be. And this is another level of abstraction and this deductive reasoning here. So if I showed this proof to my 7th graders, most of them are going to say, why are you making this so hard? I know it's 180 degrees. This doesn't mean anything to me. But when you show this to the older adolescent, and they're prepared for this because of activities that we've done, where they're used to justifying their reasons, and we've taken them slowly along, about why it's important to know why things are actually true, because other things will happen. Now they're like, oh, now I see why that happens. But they still have this visual in their head. They still have this in their minds. They still see that. But now they have a deeper level of understanding of what that is, and they appreciate this for what it is. This is not the way to get them to understand that it's 180. But it's a way to help them understand, help them to have a deeper understanding of the truthfulness of that. Students find the area of a square, they can do that. They can find the area of a circle, they can do that. But what about that orange area there? We don't have a formula for that corner looking half round, half kind of looks like a triangle things. We don't have a formula for that. But how can the students can still find that by taking the area of the square and subtracting away the area of the circle? They can find that strange area there on the end. In other words, we not only have to give them the tools to do the skill work, but then how do we apply that in new and interesting ways? And once you kind of see this trick, and I'm calling it a trick, but really it's an important mathematical concept. But kids will say, "Oh, I know the trick to this one." Once you learn that, then when you see something new, you're like, "Oh, I can apply that," and you start to build up this kind of little toolkit of things that you try. It's kind of like if anybody here has ever done like logic puzzles, and once you kind of, it's hard for kids to fool me now with a logic puzzle because either I've heard it before or I've heard something like it before, and you kind of know where to go to solve those things. And I think the same thing mathematicians do. Hey, I've seen this before where I have a weird shape that I don't know. I wonder if I can compose it of 2 other shapes. I wonder if instead of adding things, I wonder if I can subtract. And now we're really thinking about how to apply things in new ways. And so, again, geometry is a really straightforward way for them to do problem solving because, again, the answer is right in front of them. While this still requires a level of complexity to solve, it's not the same thing as having something like, a train left Minnesota going 300 miles an hour west and another train left the other direction. Like it's really hard to visualize exactly what's happening to be helpful. But here you have square, circle, that's what you have. Go ahead and think logically with those. There's a lot of other materials that we have in Montessori, which really here, we're taking, how do you find the area of the circle? Rearrange it into a rectangle or something that's a lot like a rectangle. And in this case, if you look on the left, it looks like a parallelogram with a curvy bottom. On the right, it's not so curvy. Same size circle, what's the only difference? We split it up into smaller pieces. What would happen if we made a circle with 100 pieces? Boy, that would sure seem like a rectangle. Why? Well, and we could explain that. And all of a sudden now, we're not only doing this idea of breaking things up into rectangles, we're talking about the idea of limits. This idea that if you work with the infinitely small, but you have an infinite many of them, then you can actually get results that you wouldn't be able to do otherwise. And for elementary, we use their imagination. I looked it up in my elementary album this morning, and it said, there's an activity where the same thing is done, not with this inset, but there's an activity that's done, And it says, imagine if you had 100 or 1,000 or 1,000,000 pieces, can you see that it would be a rectangle? And we just kind of leave it right there, which is good. That's a great preparation for that. But now for the adolescent, we can take it further and really emphasize the fact that, okay, what is happening? How do we know it would actually be a rectangle? Yeah, it probably would be a rectangle, but how do I know that when I get to infinity, it would be an actual rectangle? And now we're talking about philosophy, right? Things that the Greeks were talking about, things like Zeno's paradoxes and all this work throughout history that's been done. We start to talk about in a more formal way because we have a different goal. Yeah, I want my kids to know the area of a circle, but I also want to prepare them for the ideas of calculus, which they're going to be doing 2 or 3 years down the road. And why not do it with a simple material, with an idea they're already familiar with? It really helps. It really helps strengthen their way of thinking. And so this is what it would look like in a calculus setting, where we want to find the area of the circle, the half circle, or the area under a curve. What do? Split it up into rectangles. The same thing that we've been doing since elementary, where we take whatever shape, we build it into a rectangle. We take the hexagon, we make it into a rectangle. We take the circle, we make it into a rectangle. And now we're doing the same thing here again, but we're doing it with some more formal language, which you can definitely do. But the formal language comes in after they have an intuitive idea. And the intuitive ideas of this comes in very, very early. So when people say to me, they're like, well, they already know the area of a circle. Why would I do this activity with them? Why is it important if they already know the formula, where it comes from? Because they're going to be using that idea again and again and again. And if they don't have the idea with something that's simple, then I get my kids when they come to calculus or advanced algebra, and if they don't have a good geometric understanding of what's actually happening behind the symbols, then when we want to manipulate the symbols in a new way, it's just built on a house of cards. It all collapses. They don't have the thing from which to draw from to come up with these new conclusions. They don't have the mental flexibility because they never actually work with the material itself. They've only worked with the abstract. And so whenever possible, we try to link everything we do to geometry. Here's 2 students working on algebra. They're working on factoring, but they're doing it through geometry. They're doing it in a historical way, the same way that it's in Euclid's Elements, I believe, book 9. I always forget which book it's in. But then it went to the Arabs, and Al-Khwarizmi really refined that work and invented algebra. But it's all done through geometry because you can see it. You can break things apart. You can put them together. You can calculate when you can see things. And so by tying these things back to geometry all the time, it really gives our students a huge advantage when it comes to doing the more abstract work, because that word abstract means to draw from. And if students don't have something from which to draw, then they really aren't doing work in abstraction. They're just pushing symbols around in their head. They're not really working with full and complete understanding. And that's what we want for all of our students. That's the most important thing, is that they actually understand what they're doing. And when they understand what they're doing, then they'll be flexible with their ideas. Then they're going to love math. They're going to actually enjoy it again. I always wonder what happens when kids are really young, they love math, and then something happens. And I'm not exactly sure what happens, but I think we lose, because kids are so good at it early on, that we tend to move to, as the adults, we tend to push them towards abstraction too quickly. We tend to remove those materials. We tend to say, well, you can do all this with your imagination, where it's not grounded in reality. And then if they get stuck, they have nowhere to go back to, then they feel frustrated. Then they feel lost. They feel like, well, it used to be easy. Now it's hard. There's something wrong with me. And we want to make sure that students don't get to that place. And if they are in that place, believe me, we can bring them back through hands-on work, through activity, and through doing math the right way. They can rediscover that love for math, and it might take a while, but the adolescent does get there, and it's really great to see them come around. And I think geometry is a great way to do it. Again, it's very practical, it's very hands-on, especially at this age, where we want kids doing hands-on work. We want them building and constructing and designing. Geometry is a natural thing for them to do. So if they're doing that, then we can bring in a more formal study, but one that's appropriate for whatever age group that we're working with. So I think I'm going to stop there, and just to say, don't neglect geometry. It's awesome. It's so much fun. And I'm happy to, as about 5 minutes or so left, I'm happy to take some questions or or any comments that you'd like to share. So I see somebody said something in the chat. The algebraic area worksheet. Yeah, the ones that the students were working on there. Yes, I can try to find that and we can get that out. Taylor, we can do that. If you want to remind me of that tomorrow, I can see if I can find that. I can also share out the I think I can share out the hidden cubes activity. It's if you have the geometry book, if you have this guy, if you have this, it's in there. The hidden cubes activity, but we can provide that though as a PDF somewhere, can't we, Aaron? Probably. I mean, if people are interested in that one too. Yeah.
Mike, thanks so much. Great workshop. That was really fun. I love going through that cubes activity. That's so cool. Every time I hear you do it, I'm like, oh, cubes. I'm going to do it myself in my own house. And every time I forget, but I'm going to do it one of these days. So fun.
Well, I love the fact that you can discover really complicated looking formulas by just using very simple ideas. And it's something that I think that just gets overlooked a lot of times. But once you learn how to do it with something, quote, simple like that, where you can see it, it's hands-on, then when students are working with something that's more complex or abstract, they're like, wait a minute, I can come up with a formula for this. I understand how to express myself mathematically. I know how to be precise now. So it really sets them up well for the work that we want them to do later on. So yeah, I enjoyed that too. It's really fun.
Well, and the whole idea of just, getting kids excited again through geometry, you start to lose, kids start to like not feel too excited about math and kind of lose that excitement for it. But yeah, I love the idea of getting them re-enthused with geometry. That's fantastic. So any recommendations? This is from the chat. In implementing a homeschooling cooperative setting? I don't know.
What is, can you, Rowan, can you explain what you mean by homeschooling cooperative setting?
Hi, this is actually Bridget. Rowan's my son. He got on. Yeah, we have a homeschool cooperative where we meet once a week, and my kids were actually in Montessori for up until COVID. So yeah, we're basically trying to just continue it. And I mean, I'm thinking basically what I'm wondering is it possible to buy the entire set, review it ahead of time, or is there, and then go through the activities with the children from the book? Or is this more kind of like must be a trained Montessori guide?
Yeah, no, I write we can definitely send you, if you contact Aaron or Taylor, they can send you some sample lessons so you can kind of see what it's like. I really try to write everything from the point of view that, I try to tie it to what's happening in elementary Montessori, but I don't assume that anybody, teachers or adults, know Montessori ahead of time.
Okay.
It's really about, because when you come to adolescence, you're not going to teach, even though things might be based on elementary lessons, or I might have to give the same lesson I would in elementary, you can't do it the same way as elementary.
Okay.
Just like I showed with that spiral, like every age group has its own way of presenting. And so I just assume that students don't have this stuff previously. And if they do, it's great because they have a deeper level of understanding of things. But most of my schools I've been at, maybe a third have been trained have come from Montessori.
Oh, okay.
And so that's really where my lessons come from. So yeah, we're happy to share some lessons with you and see if it'll make sense for your situation. Yeah.
Okay. And what would you estimate is the preparation time like that requires for you to be able to convey the activities and the lessons appropriately? Like,
so much of it depends on the lesson itself. I know that someone sounds like a
Okay.
cop-out answer, but some things are just
Yeah.
very straightforward because they're follow-up on previous activities.
okay.
And others are just like, this is a main idea, so I'm going to really spend some time with this and have kids work with it. But you can do it in different ways, and it depends on how the students want to work. So sometimes I'll have a group of students. I might be in the same class, and I usually give my lessons to very small groups or individually to the students. And for like one group, like they want me to sit there and kind of go through all the steps with them. And we kind of do it together. Other kids, it's like, I'll do it as an activity and say, here, try this. I'll come back in 15 minutes. Let me know what you got. And they can really work much more independently on it. It really depends on the topic as well as how your students want to work, I think. I don't think there's one right way to do it.
Okay, thank you.
Sure, you're
So
welcome.
we've come to the top of the hour. I do want to bring one more question to your attention, and then maybe anyone who needs to go. This will all be recorded, and it will, like Taylor said, it'll be put on the YouTube channel for tomorrow. But Noelle asked this question: what's the simplest way, if possible, to engage parents in developing their children's mathematical mind?
Gosh, somebody asked this a while ago, and it wasn't me who had the really good answer. But I think it's just asking your students. There was something like, just asking your students questions, like always doing math. Like, you're driving in the car, and ask them to figure something, figure out something with the mileage or the speed, or you're going to the store to buy something and have them just work, do some estimation, work things out. I think it's really just having conversations with the kids. I don't think they have to teach any specific lessons, but I think having math be something that is done, something that is fun to do, something that kids can do, mentally, and it's just a way of thinking. I think just asking the kids questions and really just having those conversations is probably the most important thing to do, because when you're with your parents, that should be the friendliest, safest environment that you have. And if you see that your parents are asking you questions like that, then it just becomes a natural part of life, not something you just do when you get to school because you're made to do it. But it's just like, hey, we're just thinking about questions. So I think that's just a great thing that parents can do with their kids.
Okay, I said that was the last one, but I actually there was one more comment that came up that I just wanted to bring up. And Stephen Rose said, I tend to teach algebra and geometry, like more separate.
Mm-hmm.
And so I'll need to work on and think about how to base the algebra on geometry. And so it just made me think, like, what other examples, Mike, do you have?
Sure. Yeah, no, that's great, because just things like, so you're working with supplementary angles. You're working with supplementary angles, and those are two angles that add up to 180 degrees. So a lot of times you'll see questions where it's like one angle is 30, the other angle is X. Kids look at it and say, oh, it's 150. Okay, great. Well, instead of putting 30 degrees down there, why don't you put something like 46.392 degrees? Now all of a sudden the students can't do that mentally. They have to set up an equation. So how will we set this up? X plus whatever equals 180. Or if they just do, oh, it's 180 minus that, which is probably what they would do, they're already using the idea of the inverse to solve this equation. Great. What if you put something like one angle is 2x plus 5, the other angle is 37 minus x. Now they're setting up an equation where they have to combine like terms before they do that. If you have vertical angles, one angle is x plus 10, the other one is 4x. Now you're solving an equation where you have x's on both sides of the equation. You can put quadratic equations in there. You can do all kinds of situations where just through the geometry, solving questions in geometry, you're using the algebra skills to go ahead and do that. Yeah. And then, like I said the other day, we're doing ratio and proportion, and to solve for the missing triangle. But we had ones where they were embedded. I'm going to draw this real quick here. I know we're running out of time, but I'm just going to do this. I'll pull it up to the screen here, like this guy right here. So these are similar triangles embedded in each other. Solve for x. You end up with a really cool set of equations. And then if you switch the x and the 5 around, then you have a totally different way to solve for x. And so just doing something where kids already know ratio and proportion, but now they have to find the missing side, you get all kinds of different equations coming out of there. So I just try to find any way that we can. Oh, I'll say one more, sorry. It's doing graphing, where you graph, wait, to remember how this goes. You graph the circumference of a circle, comparing it to its area, or the radius compared to the area, and you do it on the same graph, and one is linear, but the other one becomes the parabola. It's just really interesting when you're graphing area as compared to perimeter when things change sizes or radius. And I've seen kids do it on the computer because they can do more stuff on the computer than me, and they have like the sliders and the little geometry program, and then they're doing the graphing right there. They're doing all this exploration of algebraic concepts through studying geometric shapes. Then they get to volume, and they're talking about proportionality in 3 dimensions, and you get different shapes there. So then it's like, hey, why would you ever want to graph anything? Let's see what's happening with our shapes. All kinds of really cool stuff.
That's great, Mike. I really appreciate that answer because I think it also addresses too how students, they may get geometry better, they may get algebra better. And so it really helps to lean into the student strengths. Thank you so much. It's been great. Thanks, everybody. Appreciate you all. Check back with the Math Institute. We've got lots of workshops coming up over the summer. We're going to keep Mike really busy, lots of great topics. So please check that out. And thank you
and
all
for the
that you
workshops
do.
over the summer, just so everybody knows, I'm going to be doing them twice a day, once in the morning here in the States, and then once in the evening, because I know we have a lot of people that are international, and we're trying to find times that work better for people if they want to attend the sessions live. So keep an eye out for that. We're trying to do more things at different times so we can accommodate more people. So thank you so much for joining. It's so wonderful to see all of you here. Just appreciate it so much. Thank you.
Thanks, Mike. Well done. Thanks, Taylor. Talk to you tomorrow. Good night, everybody.
Good night,
Good
everybody.
day.